So we left off after discussing Mergesort, how it works, and I briefly teasered how fast it is, but I wanted to do the analysis without having it in the last few minutes and rushed. So let's have a look at this again in a little bit more detail. What we do here is we count some costs that are reflecting the actual time on a word RAM. Remember our model, the word RAM, we would count every individual instruction as one time step. But that's very tedious to write down our algorithms at that level of detail, and sometimes it's not so clear if changing the code slightly would make this better or worse. So we'll stay a bit more higher level and instead count something that will definitely show up in the leading order term for the true cost, but is a little more abstract, more manageable. I will count this elementary operations. In this case, we picked the number of element visits, because that's also something we can compute for other sorting algorithms and compare the two. So an element visit, you can think of it as just a read or write to an element. And we'll do, in one merging round, we'll do 2 of these. You have to read the element when you find it in its run at least once, and you have to write it when it is the minimum and goes to the output. Now, you will read some elements many more times, but we count this as a single visit, and the reason has to do with caches and computer architecture. In a way, think of the visit as having a pointer to the element. Once you have that pointer and you keep that in a local register, you don't really have to pay for bringing it there when you later access it again. It's something that much more closely mimics actual running time than just counting the number of instructions in this case, because memory accesses on real machines tend to be more expensive than operations inside the CPU. The word RAM doesn't make a distinction. It says it's unit time. Whether you add up 2 numbers or you load something from memory or you store something, it all costs 1. Real hardware tends to be different, so memory accesses, especially writes, are usually more expensive. So that's the second reason why it might make sense to count element visits here. It's closer to what hardware does that is not just the word RAM. It kind of lives a bit in between. The third reason is it's a clean measure that's easy to explain. So hopefully. So we have a cost of 2 n element visits for 1 round of merging, where n is the size of the result. If we merge 2 things and the outcome has length n, then that's the cost for that is 2n. The total cost for merge sort are then written as C of n. So that's the total number of element visits when I start with something of length n. So when I start with A0n. And we write this as a recursively defined sequence. If n is at most a single element, I don't have to do anything. It's already sorted. And otherwise, I have to split it into a left part and a right part and then merge the 2. Now, the splitting doesn't really cost anything. It's just it costs 1 step here. We ignore this because it's not an element visit. But it's very, very cheap. But the 2 recursive calls, they have, again, costs of merge sort. And how much is depending on how big these 2 parts are. And if you work out the exact counts here, you see that one is n half rounded down and the other is n half rounded up. If n is even, then the 2 are the same. If n is odd, one's 1 bigger. Right? So in general, this is the formula. It gives you the number of element visits for merge sort. You can unfold this recurrence and compute what C of 10 is, for example, from just this definition. So in a way, we're done, right? This is a complete description of the cost of merge sort in our metric of element visits. But in a way, it's uninformative. It's unclear. First of all, if you wanted to compute C of 1,000,000, it already seems like quite a tedious task. A computer could still do it quickly, but it's kind of annoying. And we don't get a good intuition if we have this recurrence and some other algorithm with a slightly different recurrence, it's unclear which is better. So what we're after is a more concise, compact description of this function, c of n expressed directly as a function of n. Now, unfortunately, there's a problem. If you try to do this exactly, this function is really, really complicated. I wish I had the plot of this, but you can maybe imagine, because of this rounding up and down, things happen with a certain regularity. If you have a power of 2, then things nicely work out to be even always the same. But if you're in between a power of 2, you sometimes get this rounding up, rounding down. So you have a weird oscillatory behavior in some terms. And so this function, what I'm saying is this function is just very complicated. And it's almost the best way to write it exactly is already like this recurrence, which we found not too helpful. So what we do is approximate it. And that's where asymptotics comes in. It's an approximation for large inputs. So what we're eventually after is something like this tilde notation. Now here I could actually express this exactly, but that's a bit, it's only for the powers of 2. So we'd like to have an expression like this. The most precise asymptotic notation, asymptotic approximation that we looked at was this tilde notation, which means if I divide this by that approximation, the ratio converges to 1. Now in this case, what we simply can do is restrict our attention to some input sizes and hope that the ones in between don't behave too dissimilar. The ones that are easy are powers of 2, because then all this rounding never really happens. It's always an even number, even if you go down recursively. So if you insert 2 to the k for n, then this n half rounded down, rounded up, both becomes 2 to the k minus 1. So these two terms are the same. That's why we get 2 times the recursive call. And then this is just inserted, but 2n, that's just the same as before. Okay. Now the magic happens in the next equality, and so maybe it's worthwhile unfolding that a little bit. At this point, I'm just starting again from the left. And so I'm inserting the recursive definition at this point one more time. We used it once to get from this to this. Okay, so I'm assuming that k is not too small, then we get what's after the first equality sign? If we insert this one more time, for this one, we get 2 times, and then what we had here, so another 2 times c of 2 to the k minus 2 now, plus this term where we insert k minus 1. And don't forget to carry on this one. Okay, is it clear how I got to this step? I'm inserting the recursive definition. Now you can keep going like this, that's one thing. And you can try to spot a pattern. And for that, it's insightful to expand this multiplication. So we have 2 2's in front of this. Sorry, 2 to the k minus 2. And then this one, I split this up, so it's 2 to the 2 times 2 to the k minus 1. Let me keep this one. Now, as you may see, these are powers, so we can just add those up. And it turns out in both cases we get the same get the same term. If you further insert the expression, you will always get the same 2 to the k plus 1, because you always add a factor of 2 and make the second factor by a factor of 2 smaller. Okay, many factors in that sentence. You make k one smaller, but you add a factor of 2 outside, and the two things just cancel. And this one, you keep inserting until eventually you will hit the first case. And so then you just multiply this by 0, and it's all gone. So if you summarize what we get from this is just these merging terms. And here I spelled them out, but really they're all the same. It's all 2 to the k plus 1, and we get k of these. So that's the way of writing the result. Okay. So in this case, if we resubstitute what k and n are, so if we replace 2 to the k by n again, and k by log n, you solve n equals 2 to the k for k, right? Then you get this result, 2 times n log n. And again here, lg means log base 2. That's definitely theta of n log n, which explains why the worst case was as we had it on the Slido question. You have to remember this from last week now. What's a little more tricky to argue is that 2n log n is also an asymptotic approximation. This doesn't follow directly from our computation. We've, strictly speaking, only shown that it works for powers of 2. There are separate arguments. You can basically take c of n, subtract 2n log n, get a recursion for that, and bound it. But that's, I would say that's beyond at least our interest for this module. I think you could do it. It's not much more complicated than the recurrence we've just solved. But let's ignore this for now. We'll just pretend we have shown this, and we'll be happy with restricting Mergesort to inputs of power that have length power of 2. Okay? But let's keep this number in mind, 2 times n log n. Any questions on the analysis? Don't have a Slido question for this, but who has seen something like this for Mergesort before? Some analysis of that kind? Recursion? I mean, people probably have seen the master's theorem if you had some undergraduate algorithms class, which is a way to get to the second bit. Very few people care about the constants in front of it, which is a shame because it allows you to compare this to the next algorithm. Pardon?
Did you prove the master theorem?
We don't need it. It's a way to automate the solution for some recurrences. There's good references to look it up, but we don't really use it for any of the upcoming things. So I felt it's not needed. But I can send you some references if you're interested. There's good books that explain this well. Now, putting all together what we learned about Mergesort, we've seen that it has theta n log n running time in the worst case, measured in element visits, but that's also true for the true word RAM cost. This will turn out to be best possible, but we haven't touched on that yet. Another useful property in practice that we'll come back to is that it is a stable sorting method, which means if you have several objects that compare equal, that are A is less or equal B, B is less or equal A, you would say that means they are equal. But it could be bigger objects. Remember the example I brought up last week, I think. You're sorting a list of employees by gender. There will be many duplicates. There's probably just a handful of different values, say. But it would be useful if you could do that and keep people in, say, sorted alphabetical order, what you've done first. So you can sort by last name first, then sort by gender, and then you would have, say, all the women sorted by last name. If you do this with an arbitrary sorting method, it wouldn't work like this, because if things are equal, they might end up in arbitrary order. But if a sorting method is stable, it guarantees that things that compare equals stay in the same relative order as they had in the input. And in Mergesort, you can imagine how you can achieve this, because merging can be made stable. The trick is just very simple. If you have the two runs and the smallest elements compare equal, you just take the left one first. Take the left one first. We add the output to the right. But if you build the output from left to right, which means the thing you put in first is to the left. So if you take the left of equal elements first, it will remain in the same relative order. It's useful to play this through in an example and just make have a few numbers that are equal but use different color, and then you can keep tracing the order of the colors. Maybe not for now. Okay, the last bit, it has again to do with the fact that while we all love our word RAM abstraction, sometimes we need to look deeper, and real computers are not exactly word RAMs. They have other things like memories, memory hierarchies, and caches. Without going into why that is, what the consequences of that really are, it happens to be good to have sequential access where you move one step after the other through an array, as opposed to wildly jumping at random positions. And the reason is just caches work by bringing contiguous blocks of memory to your cache. So you have one block loaded, but then you use the entire block before you need the next one. That's what cache is like, and Mergesort happens to satisfy this. It always works sequentially. There's a downside in the merging we discussed. It needs a buffer area to produce the output. In the drawing on the slides, you don't see that so much, but really, Mergesort, the merge method that we have, gets as an input an array with the two runs in, and has some output array where it writes the result to. Again, the little devil on my shoulder says, no, you can't tell people something that's wrong. It is possible to do merging in place without extra space, or very little extra space, and still do it in linear time. But these algorithms are absurdly complicated and fairly slow. So while possible in principle, we have better methods for that. So it's all the practical implementations that are really fast use extra space. There's some methods even in practice that build on Mergesort and try to not use that much space. They become slower, but it's possible. So I felt it's worth pointing out. It's not something that is usually taught in undergrad classes.